In order to talk about neural networks, we need to know about the building blocks of neural networks, and those are perceptrons. Now, you can think of perceptrons as a very simple form of neural network or as the building blocks of networks, because a single perceptron is very similar to a single neuron. This little cartoon depicts an image of a neuron that you would see in a typical multicellular organism. Now, from a biological perspective, there's a lot going on in this neuron that is irrelevant to us as AI practitioners, but I will point out that we have this special outgoing portion of the neuron called an axon, and then there are these various little tendrils which we can think of as incoming pathways, which are dendrites. Now, we typically don't use this terminology when speaking of artificial neural networks. What we do is we think about the point where the dendrites would connect to other neurons. So what happens is the axon of a neuron leads to some tendrils, and we could have another neuron here, and the axon of one neuron would touch the dendrites of another neuron, and the sort of space between where information is transferred is known as a synapse. So how do we abstract this for the sake of artificial intelligence? This simpler diagram shows an individual perceptron or neuron or node that could be part of a larger neural network. But let's analyze it on its own first. So here we have several inputs. These are similar to the dendrites of a biological neuron. And then we have an output, which is something like the axon. Specifically, for our artificial perceptron, all calculations will be done in the form of numbers, so numerical values. So I'll have several numbers being input here, and I'll label them like so. And so here I've used subscripts to denote the individual numbers, but we can also think of this collection of inputs simply as a vector of some length. And then we will have an output from here, which I'll label O. So we have our 4 incoming values in this example and a single output value. Now the question is, what use is it to take a bunch of numbers and produce a number as output? How do we do this, and what can we actually do with it? So another component of this perceptron are what we call synaptic weights. And so these are associated with each of these incoming links. And so I'll label them. These weights are meant to model the strength of a connection in a biological neuron. So higher weight values mean that the numerical input will be propagated more strongly, whereas weight values close to 0 will reduce the strength of the input, and you can even have negative weights, which flip its magnitude. And so what happens in the neuron is we will sum up all the incoming values. So what are the actual incoming values? Well, they are the products of the inputs and their corresponding weights. So here we'll compute the sum of n equals 0 up to 3 of I sub n times w sub n. So we will sum these values, and this gives us a momentary calculation here. That is not the final output. So there's actually one additional step here where this sum gets processed through something called an activation function A. Now there are many different activation functions, and the choice of activation function can actually be quite important in different network models. But for this simple perceptron, our activation function will be also very simplistic. it'll simply be what we call a threshold function, one that if you plotted it on an XY axis would look like this, where the point where you have a jump is at x equals 0. So in other words, if this sum is less than 0, then the output here will also be 0. But if this sum is greater than 0, we will output 1. And typically, an actual output of 0 will be on the 0 side. So this is an open gap there. So this output equals the activation function applied to the sum over the different inputs and weights. Now we have one more additional thing to consider here that is currently missing from this model, and that is something called a bias. So we typically have an extra input or sort of simulated input to every neuron, which has a constant value of 1, and the weight on this link is a special weight known as a bias. Now you could also model this differently. You could say that we input a bias value, but having b times 1 is equivalent to that. So however you want to model it. So you can treat the bias as an extra weight, or you can have it as a separate component, in which case it would look like this. So this is how we take a collection of numbers, in this case 1, 2, 3, 4, use some math to then get an output. So we're just computing a simple function, and for those familiar with linear algebra, you'll recognize this as a dot product. So if I have I as a vector, and if I have the weights also as a vector, then this formula here is equivalent to the activation function applied to I dot W plus the B. So different ways of writing the same calculation, you get the same result either way. But now the question is, what is this actually useful for? Why would we do all these calculations? It's a nice, albeit simplistic, model of a biological neuron, but what does it actually do for us in terms of artificial intelligence? A common goal in artificial intelligence is to be able to classify things. Humans are very good at classifying things. We would like computer algorithms that can also classify things. And so what sort of things will it classify? Well, let's start with a simple example of points in a two-dimensional space. So I have a perceptron here which takes two inputs, x and y coordinates, and there's also a bias. And since we only have these two inputs, I've also labeled the weights weight sub x and weight sub y to make it clear what they're associated with. So if I have a 2D space like this, so this is our standard y-axis and this is the x-axis, then if I put some points in here, I would like to be able to determine if these points belong to group A or to group B. Now, a human can see that there is a clear division between these points, and so how can this perceptron perform the classification for me? Well, a perceptron essentially defines a linear decision boundary. So how does it do that? Well, let's assign some specific values to these weights and see what happens. So let's keep things simple to start with, and we'll just say that the bias is 0 and that weight x is negative 0.5 and weight y is positive 0.5. And so given these weight and bias settings, what does this perceptron actually do? Well, the sum is computed here. So what we're actually computing sort of at this point before we pass through this threshold activation function is the following formula. Well, for these specific values, that is negative 0.5x plus 0.5y. Now keep in mind that this threshold activation function has a jump at the 0 point. So if this value we're computing is greater than 0, then we'll output a 1, otherwise we output a 0. So really, this formula is most interesting at points where it equals 0. Since we have an x and a y here, we can actually move the variables around to get the equation for a line. So if I add 0.05 to both sides, then I get, and of course the 0.5 cancels out on both sides. So really, this is just a very simple line, y equals x. And if we draw that in this space, it looks like this. And so what does this mean? Well, if I pick any of these points and take their xy coordinates and I plug those into this perceptron, then I will get an output that from this activation function of 1. Similarly, if I take the xy coordinates of any of those points and put them into the perceptron, I'll get an output of 0. So in other words, I take a point, I put it in, the perceptron either says 1 for these points or 0 for these points. In fact, I could take a point right here and put that in, and it would also be 0. So this line is a decision boundary that separates these two classes of points. And so that is the use of a perceptron, is that it allows me to do simple classification with a linear, straight line decision boundary. Now this generalizes to more dimensions, and so let's say I did it in 3-dimensional space, it would correspond to a plane rather than a line. Or if I did it in a higher dimensional space, it would correspond to a hyperplane, and that becomes nearly impossible to visualize in any sensible fashion, but it is still possible to make distinctions between points. So let's do one more example with some slightly more complicated weight and bias settings. Here are some bias and weight settings for the same simple perceptron we were just discussing. And so what we want to do is figure out what the decision boundary is for a perceptron with this set of parameters. So first we'll make the same equation we had before, and we are going to set this equal to 0 because that is where the decision boundary will be. So now we can put in the real values and then simplify. This is fairly easy to simplify. I just put the y on the other side. So any perceptron with two inputs and a bias can be simplified in this way, and then we get essentially the slope-intercept formula of a line in 2-dimensional space. We know that when x equals 0, y will equal 0.5. So the bias is basically the y-intercept. And then when x is 1, we'll have 0.5 plus 0.5, that'll be 1, that'll be this point. And that's enough to draw a line, but I'll do a few more just to make it clear. When x equals 2, that is 1 plus 0.5, so that'll be right here. And when it is 3, that is 1.5 plus 0.5, which is 2, so that would be over here. And so we get this line. So examples on one side of this line would be considered positive. And so for this particular formula, these will be the values that have an output of 1. And then examples on the other side of the line would be negative, which would have an output of 0. So there is a simple learning algorithm associated with this, which I'll show you. But I do want to point out right now that the major weakness of perceptrons, of a single neuron, is that we cannot define a curved decision boundary. Let's say that we have points like this, and so that's one cluster, and we'd like to group them all together, but have another set of points here that's sort of inside of it, and then have that be a separate cluster. There's no way to really draw a straight line that completely separates those two clusters, and that's why there are more complex network models, which I'll discuss in a later video. However, first, let me describe the Perceptron Learning algorithm, because it's actually simple enough that you can go through a few steps of it by hand. So here is the learning update rule for basic Perceptron learning. There are several variables in this formula. The first is alpha, which is the learning rate. A larger alpha means we make larger changes to the weights every time we do a learning update. However, if the changes are too large, we might oscillate back and forth rather than actually honing in on a solution. Sometimes alpha changes over time during the learning process, but we'll keep a fixed alpha for our simple example here. W is the weight vector. We will use T to indicate the target for a given sample. And so if we're really technical, this is really T sub I, where I is the input vector. So every specific input vector has a particular target, and the targets are always 0 or 1 because we have two classes we're distinguishing between. Now if we make I be a parameter to what we're going to call this function P, that'll be the output of the perceptron. The perceptron is basically a function. It just takes an input vector and gives an output. And technically the value computed by the perceptron also depends on the weight vector, but that is not shown in the notation, that's just assumed. So given all of this, we have this formula. So what happens is we'll have several labeled training examples, and each one consists of an input vector and a target, and after seeing each one, we will modify the weights in accordance with this formula. So the current weights are updated or changed to be the current weights added to the learning rate multiplied by the difference between the actual target and the perceptron's output multiplied in an element-wise fashion with the input vector values. Now this is a vector, this is a vector, this alpha times quantity T minus perceptron for I quantity, this is a scalar, so this whole thing is a single number. And so the idea is that for each input value and there's a corresponding weight, and this weight becomes this number multiplied by its corresponding input. The next weight is this same scalar quantity multiplied by the next corresponding input, and so on. So this is an element-wise update to the weight vectors, and we'll see an example of this in a moment. So using this learning rule, I'm going to walk you through 3 updates of the parameters of a perceptron. Now the perceptron has to have some initial weight and bias values. I've simply set my initial weights to 0 and also my initial bias to 0, but they're often randomly initialized to some other small values. In more complex networks, the way you initialize your weights and biases can be very important, but it won't matter for our simple example here. So our starting weights and biases are all 0, and this is once again a perceptron that only has 2 inputs corresponding to x and y and a bias. And this column shows the points, the coordinates of points in the 2D plane, and then these are the target values. And so the targets here are 1, 0, 1, so these are 2 separate classes, A, B, A. The labels are arbitrary. So let's see what happens as these examples get exposed to the perceptron. So if we take 1, 1, and first we have to compute what P of the inputs is. So what is the actual perceptron output for that input? So we have 1 times 0, because the weight of the x input is 0, plus 1 times 0, because the weight of the y input is 0, plus 1, so the bias value is 1, times 0, and so that is b. So the idea is that we have 1 as a sort of hidden value in our input vector here, and then b is the weight of the bias. This will equal 0, and if we pass that through our activation function, now this is where small decisions are important. We said that this is a threshold activation function where if you are less than or equal to 0, then the output is 0, and only if you are strictly greater than 0 would the output be 1. So if we take this 0, pass it through the activation function of the perceptron, we get an output of 0, and so that means that the perceptron output of 0 is different from the actual target. The target was 1, our output was 0. They are different, and so we have to do a learning update. So we will actually apply this formula here. So our target was 1, our perceptron output was 0, so 1 minus 0 is 1. Our alpha value hasn't been specified, so we need to pick a suitable one. For these examples, I will define alpha. Alpha equals 0.1. 0.1 times 1, this is 0.1, and then times each individual input value on a position by position basis. Now in this case it's easy because the coordinates are 1 and 1, and the hidden sort of bias input is also 1. Also, all of the weight values are the same, so we're simply going to add 0.1 to each of those values. And so just to note that this was an example where the perceptron output did not match the target, so I'm putting an X there to indicate that. So that's one update to the weights and biases. Let's do it again. So for this set of inputs, we have to compute what the output would be. So just to remind you, this is the value of P applied to I hat that we're computing here. So this is this formula through a threshold activation function. And so that would equal the threshold activation function applied to 0.2 plus 0.04 plus 0.1, which equals the threshold applied to 0.34, which, because that is greater than 0, it is a value of 1. But in this case, the target was 0, so we're wrong again. It's another strike, and we'll update the weights. So our target was 0, our perceptron output was 1, so 0 minus 1 is negative 1, and so we'll have our alpha of 0.1 times negative 1 times the individual input values, and that's going to be added to the individual weight values to get our actual updates. 0.1 minus 0.1 times what is the input for x? Well, it's a 2. So we're doing 0.1 minus 0.1 times 2, in other words, minus 0.2. So this actually equals negative 0.1. For weight y, we start at 0.1, subtract once again 0.1 times 0.4, which comes out to 0.04. 0.06. And for the bias, a value of 0.1 minus 0.1 times 1. Well, that just cancels out, so the bias is back to 0. So let's do one more just to finish up. So as always, we first have to compute what the perceptron's output would be for the given input. The perceptron output is simply 1. So in this case, we get the correct value. So 1 is equal to our target of 1. And what happens in this case is our target is 1, our perceptron output is 1, so this quantity is 0, so the magnitude of the update will be 0. In other words, whenever your target matches your prediction, there actually is no update. So I could go through the math, but I'd just be adding 0 to each of these weights, but ultimately we get the exact same weights after that update step. So when the perceptron is making the correct prediction, we do not change the weights at all. And so if we had more inputs in our training example, we would keep cycling through them until eventually all of our predictions were correct. And as long as our points are actually linearly separable and our learning rate is small enough, this is guaranteed to eventually happen. However, as we saw earlier in this video, there are many cases where points that you want to classify are not linearly separable, and a perceptron can simply not handle those. So we need more complex neural network models to handle more interesting problems.